So in the last lecture, we have ended at a very crucial point. We have mentioned that if I have a signal like this, x of t, that is given by x of t, that is given by a naught cos omega naught t plus phi naught. So any sinusoidal signal like this, which is having a frequency of omega naught and a phase of initial phase of phi naught and an amplitude of a naught. So this kind of signal possesses very important properties. For example, if we add two sinusoids, ultimately you'll be getting another sinusoids of the same frequency. We add two sinusoids of the same frequency. Suppose we have like a naught cos omega naught t plus phi naught with another sinusoids like a1 cos omega naught t plus phi 1. So ultimately you'll be getting another new sinusoid of the same frequency, but the phase will be different. Similarly, if you differentiate any sinusoid signal, you will see that you will be getting another sinusoid having a different phase angle, obviously, but the frequency remaining the same. So these sinusoidal signals, so they are closed under different operations like addition, differentiation, integration, and so on and so forth. Now let us take a very pertinent example over here. So let us assume that we have got a very useful electronic component. Let it be an inductor. We have got an inductor over here, and whose the value of inductance is given by L. And suppose the excitation being provided, that is I of t, the current. This current follows sinusoidal variation, something like that. It is equal to I naught cos of omega naught t plus phi naught. And we know the relationship between the voltage developed and the current. The relationship is as simple as that. This V of t is equal to L dit dt. So if you just differentiate this one, so you'll be getting minus L I naught multiplied with this omega naught. Then you have sine of omega naught t plus phi naught. So here we find two different changes. One change occurs in the form of the amplitude. If you just take a look at the amplitude, initially the amplitude was I naught for this current, for this excitation, and as far as the response is concerned, this is given by minus L I naught omega naught. So there is a magnification by some factor. The frequency remaining the same, that is capital omega naught, which is angular frequency, and plus phi naught. So whenever you have plus phi naught, so that is basically that this minus sign outside can be taken into the consideration, and ultimately what we are getting is a sinusoid of having the same frequency but different phase. So what I mean to say is that you have a signal like this, a sinusoidal signal like this x1t, which is given by a naught cos of omega naught t plus phi naught. This has been, suppose, your input signal, and in the response what you are getting is some x2t, where we can consider the corresponding amplitude is getting multiplied by some factor. So I can write it like k times a naught, and if you just incorporate this sign into the cos, then ultimately what you are getting is cos of omega naught t plus phi 1. This will be different. So the problem is that particularly when we are dealing with the LTI systems or LSI system in particular, so in that case the change in the amplitude by some factor doesn't have any such impact, because we know the homogeneity property. So by virtue of the homogeneity property, we'll be able to take care of the change in the amplitude. But the problem lies whenever the initial phase is being changed by some amount. So initially it was like phi naught, and then it becomes phi 1. So the phase is different. So in that case, it will be easier for us to visualize the signal if I observe the signal from a completely different perspective altogether. So here the amplitude is getting multiplied by some factor k, but the phase is not getting multiplied by the same factor or by some other factor. Rather, the phase is augmented by some factor, some plus minus. It's not multiplication simply. So we have studied about the LTI systems, linear time invariant system. So where we have got three different properties. One is the additivity property, second one is the homogeneity property, and third one is the time invariance property. So whenever we got a signal whose amplitude getting multiplied, so then we can easily invoke the concept of homogeneity. But when the phase is augmented by some amount, some plus minus, so then we cannot simply invoke any of the three properties for the LTI system. So therefore, even if we observe the signal, this a naught cos omega naught t plus phi naught, as our one of the input signal or excited signal. So in that case, it will be easier for us if we visualize this signal from a different perspective. So what is that perspective? So we would like to observe the signal itself, this a naught cos omega naught t plus phi naught, as the real part of a rotating phasor. So what I mean to say is that you have got a rotating phasor, something like that. That is initial axis over there. Let's consider this is the time axis over there. And what we have got a rotating phasor which is rotating at an angular frequency of omega naught, and over here this particular value is a naught, this length is a naught, and this initial angle is given by phi naught. Now we have got this particular rotating phasor, and if I just find out the real part of this rotating phasor, so how can I write this rotating phasor? So mathematically, this is in the complex plane. So mathematically, this can be represented like a naught e to the power j omega naught t plus phi naught. That is the mathematical description of the signal. And the signal that we have considered previously, that is x1 of t, x1 of t. So this is basically the real part. As you know, this is the real part of this x of t, because we can simply observe this x of t as a naught e to the power j omega naught t plus phi naught, that is basically a naught cos omega naught t plus phi naught plus j times a naught sin omega naught t plus phi naught. So now we are not observing the signal, this a naught cos omega naught t plus phi naught, simply as a sinusoidal signal or cosinusoidal signal. Rather, we are observing this as uh, a real part of our rotating complex rotating phasor. Now, what is the necessity of representing the signal in this particular form? So to understand the necessity, what we can do is we can simply consider one particular LTI system, and we have got an LTI system in particular for which this is the LTI system for which the impulse response is given by h of t, and the input to the system is your complex rotating phasor, that is x of t is equal to a naught e to the power j omega naught t plus phi naught. So we'd like to e to the power j omega naught t plus phi naught. So we'd like to extract all the features of LTI systems, all the properties of LTI systems by applying the corresponding signal in this particular fashion. So what should be the output? Output, you know, this y of t. This y of t is basically the convolution between x of t and h of t. That is the expected output. Okay. So now we know that x of t is given by a naught e to the power j omega naught t plus phi naught. So this x of t is given by a naught e to the power j omega naught t plus phi naught. So that we can represent like a naught cos omega naught t plus phi naught plus j times a naught sine omega naught t plus phi naught. So this can further be represented in this particular form. Remember that we are going to apply this signal x of t at the input of an LTI system, which system possesses three important properties like additivity, homogeneity, together linearity, and the time invariance property. So what we get is a naught cos omega naught t plus phi naught plus we have j a naught sine omega naught t plus phi naught. So I can always represent this particular thing as plus j a naught cos omega naught t plus phi naught minus the phase difference, that is pi by 2. So this can be written like a naught cos of omega naught t plus phi naught plus j times a naught cos, there you have omega naught, then t minus pi by 2 omega naught plus phi naught. So now finally I can represent the entire thing like a cos omega naught t plus phi naught plus j times a naught cos. So we have got a cos up there. Cos, okay, yeah, a naught cos of omega naught t minus tau naught plus phi naught. So now suppose I know the response of this particular system due to the signal this a naught cos omega naught t plus phi naught. So I know what should be the response of the system due to this particular thing, and that is the input that we applied, say for example. And then the input signal, the actual input signal that we are going to apply over here is basically the j times a naught cos omega naught t minus tau naught plus phi naught. That means what? If you know the response due to this particular thing, this particular signal a naught cos omega naught t plus phi naught, then you'll be able to find out what is the response due to j times a naught cos omega naught t plus phi naught by virtue of the property of the homogeneity. And if you know the response due to that, you'll also be able to find out what is the response due to this j times a naught times cos omega naught t into omega naught t minus tau naught plus phi naught by virtue of the time invariance property. And if you know the response due to this and response due to this, then ultimately you'll be able to know what is the response due to the combined signal. So that means what? If you would like to represent the signal, or if you have represented the signal in this complex rotating phasor form, then it will be easier for you to invoke the property of the LSI system or LTI system, which were not possible in the earlier case where you applied the signal as a simple cosinusoidal signal. Now coming back to our analysis, so if you have a signal like this, xt is equal to a naught e to the power j omega naught t plus phi naught, which is applied at the input of an LTI system with an impulse response given by h of t, then the output, this output is represented by x of t convolved with h of t. So mathematically, how can I represent this output? So mathematically, this output can be represented like, so this y of t is nothing but the convolution between xt and h of t. That is what, that is basically h of tau x of t minus tau d tau for all tau ranging from minus to plus infinity. Remember, what is my xt? Xt is governed by a naught e to the power j omega naught t plus phi naught. So this gives rise to minus to plus infinity h of tau. Then you have got like a naught e to the power j. Then you have omega naught t minus tau plus phi naught d tau. Now this integration is carried over tau. So obviously, whenever you find some constant is there which is independent of tau, that you can always take it outside. So what is that constant? First one is obviously this a naught. Then you have got like e to the power j omega naught t plus phi naught, e to the power j omega naught t plus phi naught. This is completely independent of tau. And what is left? This is basically minus to plus infinity h of tau. Then you have got like e to the power minus j tau d tau. So that's a very interesting result what we've arrived right at this particular moment. Now if you just take a look at this particular expression, this one, this is basically the input signal that you have applied, x of t. This is the input signal that you have applied, x of t, that is a naught e to the power j omega naught t plus phi naught. This is x of t, and what else? This x of t gets multiplied with minus to plus infinity h tau e to the power. So there you have got a minus sign. Somehow it got, yeah, minus j tau d tau. So we have got this particular thing, x of t. When getting it back, then what is left? Minus to plus infinity h tau e to the power minus j tau d tau. So obviously this is a function of what? I have missed something over here. Yeah, I have missed one particular parameter. Yeah, this is basically minus j omega naught minus j omega naught. Yeah, this is minus j omega naught minus j omega naught tau d tau. So what you are getting is this factor, this integration minus to plus infinity h of tau e to the power minus j omega tau d tau. This is completely a function of omega naught. This is a function of omega naught, and it also depends upon the value of the h of tau. So if you have one particular LTI system, you'll be getting one expression for this. If you have got a different LTI system, you'll be getting a different expression depending upon the value of this h of tau. So it's a function of omega naught, and obviously it is a function of ht. So ultimately, this can be written like h of capital H of omega naught. And that's a very beautiful result what you arrived right now. So the input signal that you have applied over there is basically a naught e to the power j omega naught t plus phi naught, the complex rotating phasor, and in response, what you are getting the signal back. You are getting the same signal back along with the factor, this h omega naught, which is a property of what? Which is a property of the system itself, because it involves h of tau. This particular integration, involves h of tau. So therefore, it's a property of the system itself, because as you know, any LTI system or LSI system can be characterized by its impulse response. So since h of tau is there in the integrand part, so obviously this is a property of the system itself alongside the frequency that you have applied. I mean the input frequency of the complete rotating phasor, that's omega naught. So therefore, we have represented this as h into omega naught. So the same logic can also be applied for a discrete time system. So there is no harm. So you can simply apply the same logic. For discrete time system, you can represent this y of n is given by summation h of k multiplied with x of n minus k. For all k going from minus to plus infinity, where your x of n is given by, a naught e to the power j omega naught n, that is a small omega naught, plus phi naught. So basically this gives rise to minus to plus infinity h of k a naught e to the power j, then you have omega naught n minus k plus phi naught. And since this summation is done all over the k, so therefore you can take all the other terms which are not function of k outside. So what are those? Obviously a naught, obviously e to the power j omega naught n plus phi naught altogether. What is left? That is minus to plus infinity h of k multiplied with e to the power minus j omega naught k. Once again, it goes for all k ranging from minus to plus infinity, and it's a function of what? It is a function of two different parameters. It's a function of the signal frequency, that is the omega naught, the digital frequency, digital angular frequency, small omega naught. It's a function of that, and as well as it's a function of the system where you have applied the signal. So once again, you are getting the signal back. X of n. You are getting it back along with what? Along with, I can write this as capital H of omega naught. So there is a significance why I have written like capital H. So in both these two cases, the continuous time case and the discrete time case, what you have got, that whenever you're applying one complex rotating phasor in this particular form, a naught e to the power j omega naught t plus phi naught, or a naught e to the power j omega naught n plus phi naught, to an LTI system whose impulse response is given by h of t or h of n respectively, then ultimately what you are getting is you are getting the signal back along with something, and that something is very, very crucial over there. What is that something? So what I get is, now I would like to correlate this one. With the concept of vector space that we have discussed in the last lecture. So basically what we have got, this h of capital omega naught. The thing that you have got is basically minus 2 plus infinity h of t e to the power minus j omega naught t dt, or in the discrete sense, this is basically h of omega naught given by h of n e to the power minus j omega naught n, where n is from minus to plus infinity. So that is the thing that we are expecting to get from the system itself when the system is excited by a complex rotating phasor. Now we would like to try to understand what is that particular function basically in terms of the notion that we have already discussed. So if we just take a look at this particular expression, the first one, minus to plus infinity h of t to the power minus j omega naught t dt, this is, so this particular thing h of omega naught in the vector space representation, that can be represented as the inner product of h of t along with e to the power j omega naught t. That is the inner product that we have mentioned. The inner product of two vectors. So over here, side by side, let me just write it down. If I have two vectors, say one vector is x1, second vector is x2, and the inner product between these two is given by, and let us assume that these two vectors are continuous in nature. So the inner product is given by minus to plus infinity x1 t x2 bar t, or is to start t t t. That is inner product over there. So here also this h of omega naught is basically what? The inner product between h of t and e to the power j omega naught. Similarly, if I consider the discrete time case, in the discrete time case what we have is h of small omega naught is basically the inner product between h of n and e to the power j omega naught n. That's it. So now we are in a particular juncture of our discussion where we have to find out, apart from identifying the inner product, what is the physical significance of this inner product. That is very crucial, because mathematically have understood that okay, this is the inner product, this the signal that I'm getting outside from an LTI system is the original input signal multiplied with something, and that something is the inner product between the impulse response and the e to the power j omega naught t. Now the thing is that you need to understand what is the physical significance of this inner product. So to understand this one, let me go to the next slide. And suppose I have got one two-dimensional vector over there, and suppose this is the unit vector. This is the unit vector. Say let it be say I. It's a two-dimensional space, and the vector itself is given by this one. Suppose this is the vector v. This vector can be represented as say v1i plus v2j. Since it's a two-dimensional vector, so you'll be having two different unit vectors, two different basis functions, I comma 0 and 0 comma j, and this v is given by v1i plus v2j. So now, if you would like to find out the inner product between the unit vector and the vector itself, the inner product between this vector v and the unit vector I, what will you get? This is basically v1 I plus v2j multiplied with what? Multiplied with the complex conjugate of the unit vector, because both of them are vector over there. So I can be represented as I comma 0, and v can be represented as v1i plus v2j, and since I and j, they are orthonormal basis functions, so vi, the corresponding inner product or dot product between these two vectors, will give you the v1. So what is that v1? v1 is basically the component V1 is a component of this particular vector along this unit vector I. So now if you just try to visualize, if this is my vector, and let us assume that we have another vector over there, another unit vector over there. This is the second unit vector. This is the j. And then what is the physical significance of this v1 and v2? So v1 is basically this particular projection, the component of this. This is v1. This length is v1 from here to here. This length is v1. This is v1, right? This is v1. This part, yeah. So this one is v1, and this one is v2. So I have got a vector v is equal to v1i plus v2j. The unit vectors are I and j in x and y direction respectively, since we are dealing with a two-dimensional vector. So v1, that particular value, the component, is basically, this can be represented as the component of the vector v, component of the vector v along the unit vector, or I can also write the basis function or basis vector, basis function in horizontal direction. Horizontal direction. So since we are dealing with two-dimensional vectors, we'll be having only two different directions: horizontal direction, vertical direction. Similarly, if you calculate the second one, this v comma j, the inner product or dot product is basically the v2. What is that? This is nothing but the component of the vector, v along the unit vector in vertical direction. So that is the physical significance of inner product or dot product. And if your dimension is small, then obviously you understand that the components are getting added one after another, and you are finding out the component of that particular vector along that particular direction. Because you have now, since you have got say you have got one particular sequence which is having a length of say 10. So if we have already discussed in the last lecture that suppose you have got a vector of having a dimension say n is equal to 10. So in that case you will be having 10 different unit vectors, like 1, then 90, then 01, then 80, then 001, then 70, and so on and so forth. So accordingly you'll be having the component along those different unit vectors or basis functions, but it is very difficult for us to visualize these 10 different unit vectors on a two-dimensional plane or three-dimensional plane. So with this note, I would like to conclude over here. The signal that I am getting, from an LTI system, from the output of the LTI system, is when the system itself is excited by means of a complex rotating phasor, is nothing but the signal itself, the applied signal itself multiplied with something and that something is nothing but the inner product of the impulse response and the frequency of the complex rotating phasor. Then what is the inner product between the impulse response and the complex rotating phasor? This is nothing but the component of the impulse response along this unit vector, or component of this impulse response along this particular frequency. So we will discuss a lot. So that is the very crucial juncture of our discussion of signals and systems in the frequency domain. And we stop over here today by mentioning that this h of omega naught, capital omega naught or small omega naught that we are getting is nothing but a component of the impulse response along the frequency of operation or frequency of the input signal, whether it be in the continuous domain or it be in the discrete domain. So with this, we would like to stop this discussion.